Hi, I'm Antonio Sala. In this video, we'll continue with the discussion on the relationship between the best linear prediction formula like this and linear models with additive noise. We will briefly review the underlying theory. There is another video on that, and we'll discuss a numerical example. If we have two random variables, we'll assume 0 mean to avoid notational clutter, but okay, we can think on incremental variables with respect to whatever the mean is. So if we know the covariance matrix, the best linear prediction, the prediction that minimizes the variance of the prediction error, A minus hat A, the prediction is this one, covariance times inverse of variance of information, and this minimum prediction error variance is given by this expression. If I call this coefficient theta, I can express the conditional distribution, in the case of normal distribution, let's say, as a mean value given by this A hat plus an independent zero mean random noise additive with this variance. So this is the way to get from a covariance matrix to an identified linear model with additive noise. If we do the reverse, if I have this model and I know the variance of the input B, this thing, and the variance of the additive noise epsilon, then the variance of A can be shown to have this formula, and the covariance between A and B can be shown to have this one. So if I put the variance there, the covariance there, and of course the input variance in this diagonal term, then I get the associated covariance matrix given this linear model with additive noise. So covariance matrices and linear models with additive noise are sort of two ways of expressing the same thing. But of course, if we have a lot of data, what we can measure in reality is the covariance between things, and the assumption of underlying linear models needs to be justified by something else. Let's discuss now a numerical example of all those expressions. So imagine that we have a covariance matrix like this. So this is the best linear prediction. This is the error variance. Well, in the formulas above, I didn't write this, but if I multiply and divide by sigma bb, then I can write this equivalent expression. So this model, when I replace this theta exactly, and I carry out the operations we discussed here, when I replace this variance and this theta, then carrying out these operations, if I sum theta, sigma, bb, theta transposed, this will cancel out this, and in fact, yes, A will recover the original variance. And likewise, if this was the covariance for a given theta, when I replace this actual theta, then I get, of course, the original covariance. So indeed, one thing is the reverse of the other. So, for instance, if I have this covariance matrix of the joint AB, this is standardized is just because it's quite common to carry out a scaling of my variables so that all of them have the same variance if they have different physical units in order to compare. But okay, we'll start with the non-standardized original units 4338. Eigenvalues of this covariance matrix are positive, of course, otherwise it will be nonsense. And the best estimate of A given B is 3 divided by 8.375. And that estimate has a residual error of 4 minus 3 squared divided by 8. This expression here, that results in 2.9. The standard deviation is 1.7, so we explained that observed covariance with this model having this theta and having this variance or standard deviation of this additive noise epsilon. And as I said, this does not mean that the real world from which I estimated the covariance actually has a linear model. We just know that the covariance can be explained by this linear model, but maybe we find something else that cannot be explained by this linear model. We need to do some kind of validation, tests of whiteness of noise, etc., which are out of the scope of this material. Now, note that with this same covariance matrix, I can estimate B from A. Indeed, just changing letters B and A in subscription everywhere in the above formulas, we would get that I can estimate this additive noise model be equal some coefficient that I know name as eta, with eta being, of course, covariance times the inverse of the variance of the input to my model, in this case A, and prediction error variance, the residual additive noise of this model, will have this variance that, multiplying and dividing by sigma AA, can be expressed as eta sigma AA eta transposed once I substitute this. So it's the same but changing A and B, as I said. So what does it give numerically? Well, in this case, back to the variance, if I want to predict B, then the best linear prediction will be 3 divided by 4.75, and the residual variance of the prediction error will be 8 minus 3 squared divided by 4. So this is the coefficient that multiplies A to get B and the residual variance, residual standard deviation. So now we can think, okay, if I have a model that predicts A from B and I have a model that predicts B from A, well, which one is true? If we were in a deterministic case, for instance, if I have this model, I would be able to algebraically obtain B like this. So I would expect that eta is theta minus 1, and this epsilon has a typical deviation of theta minus 1, the typical deviation of this other epsilon in the first model. Is it true? Well, not really. Theta was 0.375 and its inverse is 2.6, which is clearly different from 0.75. So what happened? And again, if I multiply the standard deviation of this by the inverse of theta, I would have 4.5, which is not 2.4. What are we doing wrong? Well, this is the wrong thing, sort of. Even if this is true in a deterministic sense, this is not the best linear prediction of B given A, because when I add some noise, some information is destroyed, let's say. If I have a temperature, physical, real temperature, but I get a measurement corrupted with noise, then I cannot recover with deterministic precision the original temperature. So this noise stuff makes this deterministic algebraic inverse model be different from the optimal prediction in a statistical sense. Let us draw both models to see the differences. Just to be illustrative, I will here draw some samples of the multivariable normal random distribution with a sigma covariance matrix. With this code, the important thing is here, I will draw the 95% confidence ellipsoid using g-squared formulae, which transform a circle into an ellipsoid. Details are not the objective of this material for brevity, just you will see an ellipsoid there. And the important thing is this fragment of code. I plot A, and in the vertical axis, the best prediction, eta, times A, well, the extremes, it's a line, plus minus 2 times the standard deviation of the residual error, the additive noise, so I get confidence intervals. And also, I plot B in the vertical axis, this range B, and in the horizontal axis, which is A, the mean, theta times B, plus minus 2 times the standard deviation to get confidence intervals. So let us see what we get at the end. This is it. We get that samples are light green crosses. 95% of them are inside this ellipsoid confidence region. And the best prediction of B given A, which is in the horizontal axis, is the blue line, but the best prediction of A given B is the red line. We have some confidence intervals also, in dashed lines. So if one model had been the algebraic inverse of the other, then the blue and red straight lines would have been coincident, but they are not. The blue model estimation of B is kind of the line that joins the vertical tangent points of the ellipse. The estimation of A given B is the line that joins the horizontal tangent points of the ellipse, and they are not coincident. And in fact, we may think that perhaps the true model would be the widest axis of the ellipse. Well, that will be true under some extra assumptions. In fact, that model is what is called the total least squares model, but it's different from the least squares, minimum sum of the squares, minimum variance predictors given by the blue and red lines. Details on total least squares are outside of the scope of this material for brevity, but this is it. So predicting one thing, giving another, or vice versa, inverting in a statistical sense, it's not the same as the algebraic inverse. Just as a last observation, if I standardize my variables, so I get a scaling and my variables in original units are transformed to variables that are standardized, unit variance, then the best linear prediction would be 0.53 divided by 1, either predicting one variable or the other, because when dividing by the variance of the information, the input variable, it will be 1 regardless if we choose A or B. So in standardized things, between two variables, the coefficients of both models are the same, not one the inverse of the other, okay? So we have theta equal to 0.5 and eta equal to 0.5 as well. So one is not the inverse of the other. In fact, they are the same number. This is kind of the trickiness of the inverse in statistical sense. And if we see now the plots, then we have this kind of thing. The coefficient is the same, so this angle is the same as this angle. And of course, if blue and red lines did not coincide in some units, then making a change of variables by just scaling will not make them coincide. So let us summarize. In this video, we made a numerical example on the relationship between a covariance matrix and associated linear models with additive noise. We saw that there are two of those models when I have two scalar variables. One is predicting A given B, another one is predicting B given A. We may have thought that the two models are the same. I mean, that I can obtain the second model by just algebraic solving for b in these equations, as done with deterministic equations, but that's not true. I can solve algebraically for b given this equation, but then the resulting model will not be the optimal linear prediction, the optimal inverse model in statistical sense. So this is it. We finish here. Thanks for watching.